Hello, everyone, and welcome to the next AI and Robotics seminar. So today we have Krishna Murthy presenting his work on differentiable programs and world models. He's a PhD candidate at Mila at the Robotics and Embodied AI Lab, advised by Liam Poole. So thanks for coming, Krishna, and I'm excited to see the talk.
Thanks. Yeah, thanks for inviting me, and it's good to be here. Albeit virtually. That's how talks are these days. So yeah, today my talk is titled "Differentiable Programs as World Models." And before I get into my talk, thanks for being here. I know this is a crazy busy time. There's probably 3 conferences with camera-ready versions or materials due, and there's another conference with rebuttals, and you're probably reeling off of another conference submission. So yeah, it's just squeezed right in between all of these. Thanks for making the time. So yeah, just about me. I had to show these photographs just to show that there's lots and lots of people working at Mila. There's probably a lot more, but since the pandemic, we've never got to get together. So I just have this picture on the first slide of every talk, just in the hope that we get to meet in person again. Speaking about my work, I broadly worked on 3 themes over the past 6 years. And the approximate area covered by each of these pictures tells you at this moment how excited I am about each of these themes. So this talk is going to be on one of the themes that I am the most excited about, particularly in terms of how can you use differentiable programming to improve a variety of fields like robotics, graphics, and physics. One question that I've always been, I always keep asking myself is that there's been lots of research in robotics over the last 20 years or so. We've developed a nice theory of probabilistic robotics, and we've built perception, planning, and control modules. But over the last few years, with especially the rise of deep learning, we're now at a point where we're trying to reconcile what's the place for all of these classical techniques in the current stack. Although I won't go about all of the motivations and rationale behind why I take a particular approach, just given the nature of this talk. Today I'm going to be talking about one key idea and then 2 themes that are offshoots of this key idea. So the basic idea of today's talk is going to be that you have all of these components of a typical robotic stack. So you have perception modules that just take in perception inputs from a robot sensors and then convert them into state estimates. And then you have a planner which produces plans, and then a controller that executes those plans at a metric level, in the configuration space that a robot is operating in. And you also have the environment that's outside the robotic system. So one key idea I'm going to keep reiterating is, with the advent of deep learning, we've begun to throw away all of these classical structure of these modules, and rather in favor of replacing them with heavily parametrized but non-interpretable neural networks. So you might have connets as perception modules, and you might have some fancy MLPs, or these days transformers, for planning and control. But I'm going to be arguing for structure in all of these modules. We don't need to throw away all of the theory that we've developed, but rather use that and reparameterize them into structured and differentiable programs. So you can still do learning pretty much the same way you're doing using the tools that you use today, and get much better performance, interpretability, and perhaps generalization. So I'm going to be particularly talking about 2 efforts. The first of these is Grad Slam, which is a differentiable dense SLAM system. And the second effort is Grad Sim, which is a differentiable simulation platform. But before I get into this, one segue into differentiable programming. So I assume most of you are familiar with the notion of differentiable programming, but what a differentiable program does is it specifies a function that is differentiable. So you have a forward program that takes in inputs and out constructs a differentiable function. And then you have a gradient program, or like a backward program as it's typically called, which evaluates the derivatives of the function with respect to parameters, either internal to the function or like input to the function. So typically this just involves application, a repeated application of the chain rule, and you probably use this quite often. All of these deep learning frameworks are under the hood automatic differentiation wrappers. So with that bit of background, we'll now look at a few applications of differentiable programming. Like one such work that I did now about 2 years ago. It's called Grad Slam, and this was a paper at ICRA and in collaboration with Ganesh and Liam. So for those of you who might not be familiar with SLAM, SLAM essentially is the problem of taking in images or other sensor inputs from a robot sensors and then turning them into a map of the environment and like a trajectory of the robot or the camera. And in particular, I'll be talking about dense SLAM here. Dense SLAM just means that every pixel that you see in every image should be a part of your map. So you get very dense looking maps as the ones you see here on the slide. And yes, since the deep learning boom, everyone has been even more excited about SLAM. If you think about SLAM, it's been one of the core research problems in robotics for the last like 20 to 30 years. And with deep learning, people naturally wanted to do more of deep learning with SLAM, but there's quite a few issues. SLAM is technically a sequential process, and typical SLAM systems are more heavy on the engineering side as opposed to the science. So there's a lot of science that went into designing like the theory behind SLAM. But over the last 4 or 5 years, if you look at popular SLAM systems, what they predominantly change is how they engineer all of the, let's say how they engineer the concepts that have already been established rather than like trying to do something fundamentally different. So you still rely on factor graph based optimization, and you still probably rely on feature extraction or visual inertial fusion. But all you change is how all of these interplay. And there's also a question of, since SLAM is like a very big pipeline with several moving parts, what parts of this system would you learn? And what parts would you rather just have specified? Or would you rather just learn everything end to end, like throw a neural net at the entire problem, like expect it to produce maps and trajectories? So what we did is we take a functional view of SLAM. If you just think about SLAM as a function, in particular dense RGBD SLAM, you take RGB and Dept images as input, and you run them through a SLAM system, and you get like a trajectory of the camera and a map of the environment. So SLAM is essentially a functional view of SLAM would be you take sensor data S and you just produce a state estimate M. So our key idea was, can we somehow make this mapping differentiable? What that means is, if you were to perturb the sensor inputs by some infinitesimal delta S, so this is definitely not infinitesimal, but this is just for illustration. So you take your sensor stream and perturb it by some infinitesimal value. Your trajectory and map estimate, like your state estimate, is going to essentially change by the gradient of SLAM. So if this mapping were differentiable, you can reconcile the changes in your 3D map with the changes in your sensor inputs. So you basically want to figure out a way to specify how much does my output of a SLAM system change with respect to change in the inputs. So this was all cool, and we thought this would be really easy, and we went ahead and just coded up a 10 SLAM system in PyTorch. But that's when we started figuring out that there's a few components that are inherently non-differentiable, and you kind of need to either soften them or like reparameterize them. So many discrete operations are now continuous and can give you gradients. So we kind of implemented differentiable variants of otherwise non-differentiable components. I'm not going to go into too much detail into this specific part, just because I want today's major focus to be on the other project, Grad Slam, but you can kind of look at our paper and our project page and code for more on the details of how we make all of these differentiable. I think one particular component that I personally find interesting is the nonlinear least squares optimization. Can you actually differentiate through plus trees nonlinear least squares optimization routine? So that's one part that's kind of close to my heart in terms of all of these 4 components that we implemented. But the result is, since now you have a differentiable set of building blocks, you can realize SLAM systems that operate on various 3D representations. So you have something like Kinect Fusion, which operates on voxel grid maps, and you have point-based fusion, which, contrary to the name suggesting, it operates on surface-based maps. And you have ICP SLAM, which just operates in point clouds. And all of these, they share like very similar components under the hood. So we just use those 4 building blocks that we made differentiable and compose them slightly differently to realize these SLAM systems. What's good about these SLAM systems is the accuracy of the reconstructed map. That doesn't seem to degrade. But the added advantage here is that, as opposed to non-differentiable SLAM systems, you get differentiability for free. And I'm going to talk about how that's helpful. So one very interesting aspect is that when things are differentiable, you can actually compute gradients through the system to get rates of change, or also compute sensitivity to a particular parameter. In this particular case, we take an image as input, an RGBD sequence as such, and we reconstruct using Grad Slam. Like, we pass that through Grad Slam, and we kind of get a noisy reconstruction. And the noisy reconstruction is partly because the images we use, the Dept sensor has noise. But we also have a clean version of that data set because it's all in simulation for now. I'll show a couple of real results later. So we take a cleaned up version of the same set of images and pass them through a SLAM system and obtain a reconstruction. And this looks much cleaner. And what we'd like to do is we'd like to compare both of these. And in this slide, I show voxel grid reconstructions just so that you can imagine comparisons as just voxel-wise differences. But it kind of generalizes to even points and circles. You just need to use appropriate difference metrics, like appropriate metrics for comparison. Or here, we just subtract both of these voxel grids. We take like an L1 or L2, and then this is a loss that you define over the output of the SLAM system. And since Grad Slam is differentiable, you can backprop gradients with respect to this loss all the way through to the input RGB and Dept maps. So you kind of get these gradient activations. The edges of the camera frustum that kind of expand outward, they are places that you're most uncertain about, as are edges in the image. Like you see the edge of this portrait here. I'm not sure if it's clear, but it'll become clear in a moment. What we do in the next example is we randomly just cut out a chunk through the RGB and depth images. So when you reconstruct this, you see a hole because there's no depth or RGB information here. We just replace, we just replace all of them by zeros. And we repeat the process and we get like a gradient visualization again. And if you now subtract these two maps, you kind of see that the difference between both of these is only this like central square that we cut out. What this means is you now have a way to reconcile all of the errors that happen in 3D space and backprop them all the way through to the image pixels. You can now reason about what pixels in my image kind of contributed the most to the error in 3D. So here's a slightly better visualization. We kind of spawn this occluder randomly in space. Instead of cutting out, we now add an occluder that's in front of the camera, but it's somewhere in between the camera and the scene. So you can accurately track all of the changes or errors induced by this 3D occluder all the way back to 2D. And since you have this accurate mechanism to propagate gradients, you can do things like learn to refine noisy depth. So, this is how the actual depth image must look like. But let's say I don't have a depth image. I have only RGB frames, and then the depth images are initialized either to random noise, or in this case, we just run a depth estimation network to get like an initial fix. And it's quite poor, as you can see. But as you optimize, like you backprop through Grad Slam and then use the image gradients to use the gradients with respect to depth image to compute the updates to the initial guess, you kind of get closer and closer to how the scene might have really looked like. And if you run this for a while longer, you can get like really accurate estimates. So in this case, we just start off with both the RGB and depth being noisy. So the RGB image is noise and the depth image is just a constant across all pixels. But when you pass it through Grad Slam and then you basically backprop and recompute updates to the RGB and the depth, you kind of get quite close. There's still like a few finer features that are missing, but you get a very good fix on all of these. From noise, you're able to carve out all of these details. So just before I get into the next part of this talk, the kind of takeaways here are, with Grad Slam, the cool result for us was we could take the gradients with respect to any error defined in 3D space and propagate them all the way back to pixel space. So you can do learning in pixel space. In this case, we've done learning of depth estimation or depth refinement. But you can also imagine learning like semantics that are consistent across a video sequence and things like that. There's also a few drawbacks here. The primary drawback is that Grad Slam would require 3D supervision, because the output of a SLAM system, if you think about it, it's a 3D map and like a 3D trajectory of the camera. And defining an error function over that 3D representation means you would actually need access to 3D tracking, or like you need ground truth in 3D to be able to define that. So it's kind of expensive to gather this kind of supervision. And the other aspect is that long unroll graphs might actually cause exploding gradients. So you can't keep unrolling forever and forever. Maybe you can unroll like, for now, we've been able to unroll a few hundred frames, but not on the order of a few thousand frames. So this also limits the applicability to scenes that are fairly small and contained. But those are things we're looking to improve on. So one really cool step that a few interns in our group have been taking is, can you actually couple Grad Slam with a differentiable rendering engine. So you have this input sensor data passed to a SLAM system that produces like 3D reconstructions. And these 3D reconstructions can then be rendered down to images. And you can think of this as like a very contrived autoencoder. You take in images and you're forced to generate them back through this entire process. And you can use the discrepancy between the input and the resynthesized images to define an error function, that error signal that you can backprop and like learn anything that's learnable in the way. So you kind of see an example here. I probably need to reload the slide, but yeah, so you kind of start from noise, and through this loop, you can recover the true images. This is still like just one early sneak peek that I want to show. This is work in preparation, but just to give you a flavor of where this is headed. And there's also another master's student at Concordia University who's working on material property estimation. So you can imagine Grad Slam enabling backpropagating all sorts of 3D properties back to 2D. So can you now, instead of just predicting depths, can you also predict material properties like albedo and so on? And this in a way is essential for a lot of other tasks. Like if you were to take a reconstruction and re-render it in another, like under another lighting scheme or so on, you would need these material properties to be accurately estimated. So that's like the first part that I want to talk about. And before I get into the second part, I'm happy to take like any questions. And also like if during the talk there's any questions, I'm happy to like pause and answer the questions right there. Cool.
So I have a question. Well, actually multiple questions. So I really like the differentiable nonlinear optimization layer. So if I remember correctly, you guys did the Levenberg-Marquardt step. You put it in the computation graph as a fixed step. So I'm wondering, in order to make this scalable, do you actually need to reconstruct the entire map, or do you need to focus on some key aspects of the map? Either key points or regions of interest, but perhaps not the entire thing.
Yeah, that's a good point. So our kind of motivation behind Grad Slam was that you have sparse key point based SLAM systems, and that's one end of the spectrum. They just produce very, very sparse maps. The other end of the spectrum is dense SLAM systems, which just produce very dense maps. And most of the research in SLAM has centered around what should be the right representation for a map. Like, should you use point clouds, circles, TSDF-based voxels, and all sorts of fancy representations. So ideally, having this differentiable SLAM system, we wanted to, like, our eventual goal is to learn representations that are best suited for a task. Because the idea of SLAM is not to get a perfect reconstruction. It's always to get a reconstruction that's just enough for a robot to do the task with some performance bounds. So our hope is if you can define like a specification at the end of the SLAM system, like some way you can extend this pipeline to be differentiable through to the reward or whatever way you specify performance, you can backprop and figure out which pixels somehow are important. You can think of, instead of doing a per pixel dense depth prediction, we predict a per pixel attention map.
Yeah. So I guess where I'm really trying to get with my question is, what would you say is the bottleneck for making Grad Slam scalable and able to map large spaces?
Yeah, so I actually had one slide that I cut out. it would have been great if I could show that. So one way of making this scalable is by not requiring gradients through an unrolled graph. So of late, there's a lot of push on implicit derivatives. And you can think of Levenberg-Marquardt as a fixed point iteration scheme because it's still an optimization process and it's a trust region optimization process. So under mild assumptions of initial conditions, it should converge to a local, like a stationary point. So you might want to exploit the implicit function theorem and compute derivatives implicitly. And we've had a lot of success doing that. Like one downside of Grad Slam that we've recognized over the years is that it's no longer a provably trust region method because you still reparameterize this damping coefficient update as smooth, like sigmoid variant as opposed to like a if-else condition.
Got it. Thanks.
Cool. And thanks. Very thoughtful, both of these questions. And the second piece of work that I'm going to talk about is Grad Sim. And this work has a very strong U of T presence. I can kind of see Florian, Sanya, and Kevin. So yeah, that's almost a fourth of the author list. So this was again in collaboration with a lot of people at U of T, at NVIDIA, and other places. And just to be extremely fair, like Miles Macklin from NVIDIA is he was very pivotal in shaping up a lot of the experiments and specifically like the differentiable physics side of things in this work. So yeah, I just wanted to make sure I credit him as well. So up until now, we've looked at one kind of a differentiable program that could replace a perception module. And I call that a differentiable program just because you still have SLAM specified as a program that generates an output. But in this case, we're going to look at something that's outside the robotic system. We're going to look at the environment itself. And can we come up with differentiable programs that represent the evolution of an environment? So over the last, I guess, since 2017 or so, the ML community has been doing a lot of work on differentiable physics. And the reason we kind of care about differentiable physics or like bringing in a physics engine into an inference is you can consider tasks like you have this walker, which is essentially a soft robot, and you want to figure out how to make it walk. Or in this case, you have like a pool table and you want to hit, you basically want to hit the cue ball so that this blue pool ball reaches the hole here. So all of these kinds of problems require physical reasoning. And there have been a few attempts ranging from just throw a neural net at it versus like do reinforcement learning. But of late, approaches that have been more successful are ones that explicitly bring in some form of physical reasoning into play. So people have done it by just bringing in non-differentiable physics engines and performing gradient estimations for them. That's what you typically do in reinforcement learning. You have all these simulators like Mujoko, PyBullet, and so on. But more and more of the years, people have been realizing that if these simulations are differentiable, which is if you can compute the gradients with respect to gradients of the outputs of the simulator with respect to the inputs as well as the parameters, there's more you can do. So this is one example from last year where they kind of implement, this is called Dept, and they implement a wide variety of physical simulations, both for parameter estimation and control style tasks. But one disadvantage in all of these systems is these systems need supervision in the state space. So if you think about what the output of a simulator is, a simulator takes in some initial configuration, such as the config of this billiards table or like this robot here, and produces output states. And by states, it could just be positions and velocities, or it could be a lot of other aspects. So for the soft robot here, you might have a per grid cell state. This soft robot here is actually a collection of a lot of components, and each component might be in a different state. So if you want to specify any kind of objective at the output of the simulation, it must be in the state space of the simulator. And the question we were asking is, can we somehow do better? Like, this kind of supervision is very hard to gather, especially if you think of systems like these deformable objects or more chaotic systems like cloth. It's almost kind of impossible to track each and every point on a cloth. So our idea basically was, if you think about existing approaches to differentiable physics-based reasoning, they take in a scene description and pass it through a physics engine that's differentiable, and it produces states. And it just keeps running on and on. And for over n steps, it produces states, and you have supervision defined either here or like at multiple spots along, and you can backprop all the way to figure out how your scene description must change in order to achieve a target specification. And what we do differently now is we take on a view of simulation as both being physics plus rendering. So as a human, when you look at the simulator, you kind of want to see how the object configurations change. So if I probably just tell you the positions of each object and just like print out a mess of numbers, that might not make a lot of sense to you. So because of that, a lot of simulators have some form or some way to visualize outputs. And we wanted to like tap onto this because each simulator has a built-in visualizer. Can we use this rendering engine and also differentiate through that? And what that will enable us is to, if you think of the forward process, you're given a scene description and the physics engine keeps running and produces states at each time step. And at time steps of your choosing, you can just render those states to form an image. And that's how you like get all of these videos of simulated objects and so on. And crucially, the rate at which the physics and rendering engines run need not be identical. Like you can always think about rendering much slower than the physics engine updates. But our idea is, if you now think of this physics engine augmented with a renderer, the output of the renderer is an image. So you can essentially provide supervision in image space and backprop all the way through to the scene description. So that was our initial goal for this project, where other differentiable physics-based approaches would require state-based supervision. We wouldn't need to track each like joint position and velocity. Rather, if you give an input or a target video sequence or a target image in many cases that you'll see later. And the kind of problems we're interested in is you're given like a video sequence. We're interested in two kinds of problems. There's a system identification problem where you're given like a video sequence and you want to estimate all of the physical properties of an object. And there's also visuomotor control kind of task that we're interested in, which I'll get to soon. So again, to recap, we have like this system where we take in an object specification in terms of like, its mass, friction, elasticity, and the kind of forces external forces acting on the object. And you roll them out through a physics engine, generate states, and render them out to generate like a predicted video sequence. And this predicted video sequence is compared with a ground truth video sequence. And in most cases, we do like a frame by frame mean squared error over each pixel. So we just take these images across each time step, we stack them together, and we do an L2 loss over them. And since like the simulator is differentiable, you can backprop these gradients all the way through to the physical properties. And I'll show you a few visualizations of how smooth this optimization process might be. So again, the key distinction between approaches that would use only a differentiable physics engine is they would only produce states, and you would need to somehow provide supervision here, or you would need to perform some form of gradient estimation through this other part. So one key difficulty that we had to encounter in this project, and this is where like Miles Macklin from NVIDIA is primarily contributed to this project, is how do you differentiate through a physics engine? So one way to think about it is implement a physics engine in your favorite automatic differentiation framework, and either you have a tape-based system that records all the steps that you've ever run through, or you might do something smart that PyTorch does. It only selectively records nodes in the computation graph that are relevant to the current computation. But that can just turn expensive very quickly. So if you think about a 3-second simulation with each second being split into 16 discrete time steps, and each step has 16 substeps because you want to integrate measurements over an interval, you already see like for a 3x16x16 states, this already becomes quite expensive. If you're talking about an object that has 100 vertices, for example, you're storing 3x16x16x100 vertices at for just a 3-second simulation for that one object. But a lot of our examples, as we'll show later, contain typically 3,000 to 4,000 vertices, and you can't fit it into commodity GPUs. So again, the key idea here is figure out a way to backpropagate gradients without having to store all of these intermediate activations. So the idea here is if you can come up with a constraint that the time integration scheme needs to satisfy, or here we're just writing this constraint as g, a function g of your previous state s minus and your current state s plus and any other parameters, that should be equal to 0. And those constraints would typically look like, your updated velocity or like position must be your previous velocity plus some like physical constraint about the system. And similarly, you have a constraint on velocities. If you differentiate through the system, you'll end up with like a set of equations of this form. If you can we provide one concrete example in our paper, like towards the appendix, and I'd encourage you to look there for like a concrete system, but you can kind of see why this will not require you to unroll all of these, because the gradient with respect to your previous states can be computed without having to access all of the intermediate variables. You only rely on the inputs and the outputs. So using such an implicit, it's not necessarily an implicit differentiation scheme. We apply the implicit function theorem, but a more technically correct way to call that would be the adjoint method. We just apply the discrete time adjoint method to implement like backpropagation through our physics engine. And you can realize a variety of physical systems, like not just rigid bodies, but also deformable solids. So if you look at this gear here, it is a collection of tetrahedrons, and each tetrahedron looks something like this. And each tetrahedron can expand and contract by some volume ratio alpha. So if you define alpha to be 1.3, your tetrahedron is expanding so that it's like it increases 30% in volume. On the other hand, if alpha is less than 1, it kind of shrinks. And if you look at the sphere on the right, that's again a tetrahedron. And these tetrahedrons can shrink and expand and kind of make this object move in a variety of ways. And this is something we'll revisit sometime later. So just something to keep in the back of your mind. And a degenerate case of this tetrahedron is when the volume is 0. You can just think of it as a triangle, and you can still like sort of bend the triangle or expand or contract the triangle and so on. This kind of a parametrization is useful to simulate plot. So that was about like the physics engine and like just a flavor of a few systems that we could support. And over the last, I'd say beginning 2015, the computer vision community has become interested in differentiable rendering. And what a differentiable rendering means is you have a rendering process. So rendering is basically taking in a scene specification, a 3D scene specification. In this case, it's like a 3D geometry of an object, like a mesh representation of the car, where each mesh element is a triangle, and a light. So a light source position and the intensity of the light source and directionality of the light source and so on, and a texture to wrap around this mesh. So you could think of like the same car being painted in various colors and so on. And that's what a texture essentially allows you to do. And you kind of pass this through a renderer to render an image. That's how you see a lot of graphics. But this renderer is differentiable in that it allows passing gradients back through, and you can basically update your inputs to the renderer as well as like parameters that you have within the renderer. I'm not going to go into the details of these renderers, but again, this is work from NVIDIA and U of T again. So I'm sure you'll have like quite a few friends there. But yeah, this is like the paper that you might want to look at if you wanted an example. So with this, we're all kind of set to see how we might apply this to a few system identification problems. And again, system identification is given like an initial guess on these properties, and all initial guesses are sampled uniformly randomly from like pre-specified ranges. Like for masses, you would sample mass densities from the range of, let's say, 2 to 12 kilograms per meter cube and so on. So you'd have quite broad ranges over which you would just sample initial guesses and render out a video, and that video would be incorrect. And you'd compare that with the true video, and your objective is now to run gradient descent, in this case, not stochastic. You would want to infer parameters that are as close to ground truth as possible. So one example that you see here is rigid bodies. We have like a cube that's much heavier than it's supposed to be. So it falls, but then doesn't bounce back. But after about 50 to 100 iterations of optimization, I should have put a number of iterations here, but yeah, the thing is, after things converge, you kind of end up with the true mass parameter, and then it behaves as it's expected to. This is another subtle case. You can see that the objects kind of fall similarly, but their end configurations are different. So even if the mass is correct, you need to get the other contact parameters like coefficient of friction and so on accurately. So with Grad Slam, the kind of accuracy you get is close to 2 to 3 places of decimal. So after optimization, you kind of get a config that's much closer to the ground truth. And we also do something very similar for deformable solids. You want to estimate the elasticity parameters so that you get the right kind of bending behavior as you see in the ground truth. So this is a very poor initial guess, and then after optimization, you get very close. We also do this for incompressible fluids, or here it's smoke, where there's a lot of smoke particles resting on the ground. And I just grabbed this pattern of Google Images, but I had to kind of tailor it, like run an off-the-shelf binarization algorithm. And the goal for the smoke field evolution is, at the end of 5 seconds of simulation time, it's either of 3 or 5 seconds. I'm kind of hazy on the details, but you need to get this target pattern that you see in the third column. And we get quite close on getting the course pattern right. So we went back and looked into why our, can we explain our performance by looking at the loss landscape through the simulator? And we found that, for example, for mass estimation, for an object that has ground truth mass of 1, the loss landscape through a simulator looks much smoother when compared to something through, let's say, when we use a non-differentiable simulator, but we run gradient estimation through that non-differentiable simulator. So, or here we use PyBullet, which has a much smaller convergence spacing. There's like a few tables, but since these are in the paper, I'll probably skip to the more interesting results. And just for context, how much more time do I have? I guess I'm nearly out of time.
Probably about five more minutes.
Yeah, I think let's try to wrap it up in 5 minutes.
Yep. Yeah, that's pretty much all I need. So thanks. So in this case, it's a tetrahedral mesh model that I showed you. You can actuate each tetrahedron by, you can actuate this object by expanding and contracting each tetrahedron. So we train like a 2-layer neural net that's predicting the actuation parameters for each tetrahedron, like between a range of 0.7 and 1.3. So each tetrahedron is allowed to contract or expand by 30% of its initial volume. And you kind of need to figure out at each time step how much to expand or contract. That's the policy the neural network is learning. And after optimization, it kind of gets quite close to ground truth. So the gear kind of learns how to roll. And the key thing here is we only use one image as a supervisory signal. So we take this image at the end of simulation and we compare it with the ground truth image. And we just take an L2 difference and backprop it all the way through the simulator and then figure out how the gear must move. And we do a similar thing for cloth, where we optimize the initial velocity vector through which we throw a cloth so that it approximates this ground truth. One other interesting example is a 2D walker. So instead of tetrahedrons, it's now just triangles. And this walker has been it's been initialized with a random policy. So it kind of does nothing interesting in the beginning. But then you have a target image that the walker needs to be at the end of a 3-second or 4-second simulation. And as you keep doing gradient descent iterations through the simulator, you can see that just at the end of the first iteration, it kind of starts beginning to walk towards the right. And at the end of 2 iterations, it reaches the target configuration. There's a bit more that we did in terms of analysis, but in favor of time, I'll just end with like few take-home messages. With Grad Slam, you can get accurate estimates of physical parameters from video by not requiring state space supervision. But there's still a caveat here. Your modeling assumptions need to be somehow correct. And let's say your model of friction, or when I say model, like your equations of friction or contact, when they're incorrect or they're far off from what's happening out in the target video, you kind of have this gap, which causes a drop in performance. So there's still scope to improve in terms of how you can improve things within the system. That's pretty much my kind of take-home messages. But just in summary, I guess we saw 2 kind of differentiable models or programs that can be useful, one for 3D reconstruction and the other for visuomotor control as well as system identification. And we also have seen like a few recurring downsides with differentiability. And there's clearly a lot of work that needs to be done in overcoming some of these, downsides of differentiable models. And perhaps that's where model-free approaches can kick in. And there's all sorts of exciting follow-up work that, I've been also discussing with Florian on and off about a few ways to plug in some of these gaps. All right, I probably ran over a bit. Thanks. I'll end in time, or end just 10 minutes over time.
Great. Thanks so much for the really interesting talk. So I think that there's a meeting now with Animesh, so I can send you the link to that. I'll just send you an email with that. And if anyone wants to sign up for the meeting slot at 12, then I will send you the link to that as well. Otherwise, yeah.
Sure. That's good.
Are there any questions before we sort of finish up? I see some stuff in chat.
I have a question.
Yes, go ahead, Chris.
So Krishna, when you were describing the loss landscape with respect to like the estimated state parameters, could you give some intuition? I'm a little blurry on the math here. Could you give some intuition on why gradient estimation through a non-differentiable render is like non-convex?
Sure. So when we say gradient estimation through a non-differentiable simulator, we kind of take the images rendered by PyBullet as like the reference point. So we kind of try to align all of our parameters, like the camera parameters and the object colors, textures, lights, and so on, so that we get like accurate, let's say, we have a perfect match between what PyBullet does and what we do. But there's a lot going on in terms of the renderer, and PyBullet has a slightly different physics engine as well. So it has slightly different contact models. That causes a change in the dynamics. And the renderer that's used by PyBullet is basically OpenGL based. So what you typically see in differentiable renders are the renders that you get are quite smooth, which means very sharp details on the edges. They're blurred to improve gradient flow through those regions. Because an edge is a discontinuity, differentiable renderers kind of soften these edges. But PyBullet has no reason to do that. So all of these things make gradients through a non-differentiable simulator slightly weird. It's just because the entire process is not differentiable. In trying to make, let's say, a renderer differentiable, you make a few approximations that kind of reduce the number of discontinuities, and similarly in the physics engine.
Okay, that makes sense. Thanks, Krishna.